One of the trends we're seeing more and more is research is shifting toward looking for longer amplification of longer sequences, a need to multiplex longer sequences, bring those in, looking at different splice variants, things for like using this as template prep for characterizing and doing HLA typing. And so there are a variety of kind of core PCR tools, and some of these have been around for a very long time. So you might ask, you know, why long-range PCR? I mean, this is 26 years old now. I mean, I met Wayne Barnes back when he first did this. It dates me, but some of this technology could be actually older than some of you sitting in the audience right now. But Wayne reported this, and you know, why was it important and why is it still relevant? I mean, in the old days, people were looking at just trying to clone products, and so they were looking at trying to characterize based on cloning. Now everything's moving into NGS workflows, and whether that is then taking the longer products, fragmenting those, and doing sequencing on Illumina, or using the longer products to feed workflows directly into long-read platforms like PacBio. So there are emerging needs, and I think some of the older technologies that we've been working to improve upon do still have a very firm place as a research tool today still. So what was the revolution behind long-range PCR back in 1993 or so? It's kind of a long time ago. Basically, the enzymes used for high-fidelity PCR, namely these archaeal, you know, polymerases like PFU, Vent, Deep Vent, you know, high fidelity was synonymous with finicky. They were a pain to use. They were not very reliable. They generated low yield. Their processivity of these enzymes is extremely low. They'll add 2 to 4, sometimes 6 nucleotides before they disengage from the template, so they're always hopping back on. And some of that helped contribute to, actually, I think they thought the theory was that to their fidelity. So by monitoring, they could go into a switch mode of base misincorporation, fix it with the 3' exo, and continue nascent chain extension. Other problems with it is that these archaeal polymerases, this was an observation that reported with Roger Laskin back in the mid-90s. We were the first to discover this actually through working on long-range kits, that DU and template DNA the archaeal polymerase would bind very avidly to that. And so that can actually end up being a problem down the line. So I'll explain that in a minute. So the way Wayne got around the problems of yield and specificity with a proofreading polymerase was to basically supplement TAC with a limiting amount of a proofreading polymerase. So it gave you some error correction. Basically, so if you have misincorporation by TAC, you have a board of nascent chain extension, TAC falls off, proofreader hops on, fixes the base misincorporation, and then TAC can hop back on and have further nascent chain extension. So you get longer products, usually more in the range of about, I say, 4-fold higher fidelity than TAC alone. What made these products attractive back in that era was really that for anything over a kb, 2 kb and above, you would see much higher yield and more robust performance, kind of broader application to a wider range of templates. But one downside, and I've always done this long and accurate or long PCR to be synonymous with taking a very long time. When I would set up experiments, I mean, if you do the math, right, 20 kb, 20 seconds in nature, and you know, 35 cycles, it's going to take all night. So my productivity, they thought I was working very hard. I would set up reactions at 4:30, throw them in the machine, go home, come back the next morning, run the gel. Goof around during the day, set up another reaction at 4:30, you know, kind of just continue that process. But that lag, really there's a huge delay in your time to result and analysis with that. Also, this prolonged exposure of DNA or your nucleotide pool to high temperature can result in this deamination of cytosine to uracil. When you have uracil and the uracil gets incorporated into the DNA, then you have termination of extension. Now the team at Strategene had a novel trick of throwing in a DUTPase into the long PCR mix or with their PFU enzymes, and that tended to help. But these long templates would still be subject to, deamination, and if a DU did occur, one, the proofreading polymerase would bind to it very avidly. That acts like a sponge. You deplete the polymerase from the reaction, and it also is a potent block to any further nascent chain extension. That's something that Roger Laskin and I showed in our JBC paper back in the mid-90s. So what we've done is we've kind of flipped this on its edge. We've blended TAC. It's actually a slightly precessive TAC variant with a modified proofreading polymerase. This polymerase has very high processivity, and we've mutated the uracil binding site and the read-ahead function and the amine terminus of the enzyme. So it's basically what we would call DU literate. We've provided stringent hot start for every polymerase activity in the mix, so TAC is inactivated at multiple epitopes with a cocktail of monoclonal antibodies, and we have antibodies sequestering both polymerase activity and the 3' exo activity for the proofreading polymerase. So you have a very stable mix that you can set up at room temperature and not have any problems. One thing that was surprising that came out of this mix, and some of this is from this novel proofreading enzyme in combination with the TAC, but also the buffer system utilized in it. But we saw much higher accuracy and fidelity with this particular mix compared to other long-range mixes. In fact, the fidelity measurements that we got in a typical blue-white screen kind of fidelity assay was actually very close to what we saw for enzymes like KOD or PFU alone. So we were seeing, faster extension times. We were seeing much higher yield, much more robust performance over a broader range of templates, all out of this nice, stable 4x concentrated master mix. And one of the surprises from it, too, is that we've been able to multiplex with it quite nicely and do longer templates. So we can look at, again, that came out of a project where we were looking at trying to multiplex multiple HLA loci all at one time. So going into a little bit of just the data, it's not extensive. There are a few primer sets out there that are widely used that everyone looks at. There's an 8.5 kb locus of beta globin, a 17.5 kb locus from beta globin, and a 24 kb fragment of the TPA gene. So we're looking at long range against two of the other major competitors with some of the better performing long range master mixes on the market, and you can see much higher yield at lower input quantities and also faster cycling times with the long-range supermix compared to the other products. And again, these are also 4 other comparisons against 4 other products on the market. And you see the 8.5 kb, the improved yield, and amplification of the 24 kb fragment from relatively low levels of input genomic DNA, actually, and very strong, very specific yield. So I've been very impressed with that. The other advantage of the ISO 1345 manufacturing system is it drives you and really looks at trying to produce a consistent product. And so this just kind of shows the lot-to-lot consistency and also some of the reproducibility for amplifying some of these, more challenging, longer length products with this particular mix. And again, one of the other benefits that we saw from this was we didn't need, with previous versions of this, there was always a need to include something like beta-ene or some kind of a GC-rich enhancer, and we haven't seen that with this particular product so far. Doesn't mean it, some samples may still need that, but overall, just right out of the box and as it's used, it works very, very well. So this just shows multiplexing of fragments ranging from 1 kb to 6 kb from the BRCA gene. The 6-plex here is shown in the panel over on my left, your right. So again, very flexible, very robust performance with this particular master mix. And so we can't reveal who this was with, but we're actively putting this out in different beta tests and different applications testing in different labs, and we always welcome collaborations. So we had a particular client that was interested in higher PCR product yield. They were looking at generating basically targeted panels that were feeding their long-read, PacBio system. This is the gel data that they provided. You do see some higher band intensity on some of these. Overall, what they reported back to us was they felt they saw improved product yield in faster turnaround time, which improved their workflow. And most importantly, because they were getting higher specific product, they were seeing better quality sequence data on their system. So after that, I guess, rather than asking why long range, kind of like why not long range? Seems to be a very versatile system. It has can have very diverse applications. And we think we've done a good job of capturing these different performance attributes and benefits into the product that we're releasing. And we're very excited about it.